This is a picture of Thwaites Glacier, one of the largest, widest glaciers in Antarctica. It's huge. It stretches completely across the horizon. Even from an airplane looking out the window, this glacier is so large, it covers the horizon from side to side. It's extremely thick, and beneath that ocean water that the ship is floating on, about 6 times as deep as that ship is long, there's warm ocean water reaching the underside of the ice and melting it. And that's why we're here. There's a huge impact from this warmer ocean water eating away at the underside of the ice shelf, and a lot of effects on that interface. That's what we're going to talk about today, is recent research results from the interface between the ice and the ocean along Thwaites Glacier, one of the largest glaciers in Antarctica. You can see that in this map of elevation change over Antarctica, that there's a large red patch in the left side of Antarctica, and Thwaites Glacier is right in the center of that area of elevation loss. It's already begun to put more ice into the ocean than falls as snow on top of the ice sheet. Now in the upper right here is the ice sheet. That series of lines shows how the front of the ice has, the place where it goes afloat, has retreated over the last 20 years or so. And then the gray area is the floating ice out in front, which is evolving rapidly. And here are some of the facts that have caused us to look at this glacier in particular. Thwaites Glacier was identified by both US and UK scientists as being the most important place to study for near-term sea level rise. Within this century, this glacier could, all by itself, begin to significantly affect sea level rise. Our goal is to assemble the data and knowledge and then advise policymakers. The US and the UK funded a massive effort, 8 projects and over 100 scientists, to study all aspects of Thwaites Glacier. This cross-section shows you some of the geography of the area in a stylized form and all of the different aspects of the ice, earth, ocean system that we're going to study and report on today.
So the Thwaites Glacier, as Ted said, flows into the ocean across a stretch of coastline that is nearly 120 kilometers in length. Over 1/3 of that coastline, the glacier flows more slowly because it's being stabilized by this floating ice shelf that's attached to this submarine seamount. It's about 50 kilometers offshore. As it's structured right now, this ice shelf acts like a dam, but it's not going to for very long. My team, led by Ted, is heading down and studying this demise of the ice shelf. So essentially, there are 3 parallel drivers for the collapse of this ice shelf. And the collapse of this ice shelf will result in a direct increase in sea level rise pretty rapidly. The first is direct melting by the ocean underneath. The second is the loss of grip on this submarine seamount. And finally, the third is the shattering of the ice itself, with numerous fractures propagating at ever faster rates. Our oceanography team that's on its way through Chile is going to do an intensive study of water around and underneath this ice shelf. From their last visit a couple of years ago, we already know that warm waters are flowing in off the continental shelf, shown in the pink and red arrows. They're mixing together and causing melting in some key areas, particularly that area circled in black and right behind that submarine seamount. Importantly, what this means is that the ice is losing its grip on that seamount. We have also found through satellite imagery that the ice tongue on the more western side of this area is now just a loose cluster of icebergs and really no longer influences this eastern, more stable part of the ice shelf. That connection between them, shown by the black line, is nearly gone. This split between the ice tongue and the eastern ice shelf has caused the eastern ice shelf to change its flow direction dramatically over the last 10 years. This is the area shown in black, where you can see the white flow lines are moving over towards the left and expanding out towards where the ice tongue used to be. This change in flow direction is also indicative of the loss of grip on that submarine mountain. If we zoom in on the seamount here, we can actually see the reduction in contact area over just the last few years. The green was the contact area circled in 2014, and the 2020 contact area circled in red there. The scale on that, it's approximately 15 kilometers from end to end there, but it is a very significant decrease in contact area. And we are predicting, if it continues on its current trend, using the current kind of processes ongoing, we expect that it will reduce down to near zero contact within a decade. But other things are changing and evolving, so I don't expect it to be a nice linear trend. So it could increase more rapidly, or it could slow down and stick around, and we might have another mode of failure. But we actually think that the fracturing mode is probably going to supersede that, and that will happen within a few years to 5 years. But that also is hard to put a number on, because there's so many processes going on that projecting out in a linear fashion like that is very difficult to do. I visualize it somewhat similar to that car window where you have a few cracks that are slowly propagating, and then suddenly you go over a bump in your car and the whole thing just starts to shatter in every direction. So a subtle change in the stress can cause the fractures to propagate more quickly. And there are a lot of weak zones. I identified one weak zone, but there's a few others that are potential weak zones that can transfer stresses and propagate fractures in multiple directions. And at that point, it might actually just bypass the seamount and go out towards the upper right on that figure. So it can essentially fracture to where it just doesn't even care that seamount is there anymore. And most of the ice will go off to the upper right in that picture as the fractures start to propagate, and it loses its coherent, the material just loses its ability to hold that strength, and it starts flowing outwards. But before it fully loses its grip on the seamount, this eastern ice shelf is likely to shatter into hundreds of icebergs, just like the shattering of your car's window. Over the last few years, just since 2016, we've seen fractures propagating at alarming rates, well over 10 kilometers a year for short bursts of time. Each new satellite image we get, we see deeper and longer fractures. The tips of some of these fractures actually are just a few kilometers away from where our team is headed right now. Those are the red and green dots in the satellite images and the red dot on the plot. An additional complicating factor is that underneath the red and green dots that are our field sites is weaker, thinner ice with quiescent or latent basal crevasses waiting to be reawakened. This weak zone is shown here in this cutaway perspective view, which uses a satellite image as well. And in this figure, ice is flowing from the left off the continent and out towards the right onto the ice shelf and into the ocean. And here we're looking across it at that seamount in the far back corner. You can see my writing back there. I cut away a chunk of this ice and in a cartoon manner showed what the ice looks like from underneath. The rapidly propagating fractures shown in arrows there are headed right into this area of thinner, weak ice. And we believe that when these fractures propagate into this weak zone, new fractures will initiate in different directions, leading to a more rapid demise, possibly within a few years.
For the mountain project, though, we focused entirely on understanding the processes operating in this region known as the grounding zone. And this is the region I've highlighted in red here. And this is where Thwaites Glacier first lifts off the seabed to become a floating ice shelf. Kind of understanding the interactions between the ice and the ocean here are critical to improving our projections of future sea level rise. because the processes that operate here strongly influence how quickly that grounding zone migrates inland and how much grounded ice is therefore lost to the ocean. The grounding zone on Thwaites, though, lies under about 650 meters of ice. So our first challenge is to drill an access hole using hot water so we can get to the area of interest. We were able to take the very first observations within 2 kilometers of the Thwaites grounding line itself. We found a very narrow 54-meter deep water column. So this is quite narrow because, of course, we're quite close to where the ice shelf first lifts off the bed. And we found that the water column was characterized by strong gradients in temperature and salinity. So in this panel labeled 1. The temperature of the ice base is 1.5 degrees above the freezing point, indicating that there's plenty of deep ocean heat. As Erin pointed out, there's plenty of deep ocean heat available in the grounding zone to drive basal melting. So through the borehole, we also deployed a remotely operated vehicle, and we used that to survey how quickly the ocean was moving, the ocean currents essentially, within the grounding zone region all the way up to the grounding line itself. And what we found is that the currents were very weak. They average only about 2.6 centimeters per second. And the key message here is that weak currents tend to lead to lower basal melting. So we have a picture where we have high temperatures to drive basal melting and low currents that tend to lower basal melting. So they counteract each other. So we're also able to leave sensors behind in the grounding zone to monitor how the ocean conditions change through time. And what we found is that during 2020, the grounding zone becomes warmer and saltier due to ocean conditions changing outside of the cavity. So this shows there's a link between what's happening outside the cavity and what's happening at the grounding line. And overall, what it demonstrates is that more deep ocean heat was available to drive basal melting as it arrived at the grounding line. So throughout 2020, the thermal driving, so this is the difference between the in-situ temperature and the in-situ freezing point, increased to over 2 degrees centigrade. However, using radars we deploy at the surface to measure the melt rate directly, the melt rate's actually pretty small on Thwaites Glacier grounding zone. It's only about between 3 and 5 meters per year. And this is about an order of magnitude less than we see on other grounding zones. So what we're basically seeing is, despite the high ocean temperatures, the basal melt rate is quite depressed because of the weak ocean currents. And overall, the take-home message is that this suggests that the rapid grounding line retreat we've seen beneath Thwaites has been associated with relatively modest basal melting, despite the high ocean temperatures.
So Iceland's shown in the bottom part of this slide as this long and skinny yellow robot, which again, we deploy through the borehole. And it's a great tool to get spatial pictures of the ice, ocean, and seafloor in this region, which is helpful because it allows us to really get a good understanding of the holistic picture in this hard to reach region. So here I'm showing data from Iceland along 2 transects in this grounding zone. T1, which you can see in this inset map, is the Burgundy line, and T2, which is the Navy line. So key takeaways from this is we were able to map the ice, ocean, and seafloor here over about 5 kilometers. And at T2, we were able to map these properties all the way up to the grounding line point, which you can see in the top right corner of this figure. These data depict a chaotic grounding zone where the water is warm, as previously mentioned, most of which is 1.5 to 2.25 degrees above freezing, except near this grounding line within the several hundred meters of that point, which you can see in the top right of T2, where the water is colder at about 1 degree above freezing. We're also able to see that the ice is rugged, where it has these corrugated features near the grounding line that, as we move away from, we observe these very large crevasses. And then finally, on the outer part of these transects, we see these step-like features, which can be seen very nicely in T1, where the ice is flat, and then there's a hard step up to a next level. We call these terraces. And finally, we see that the grounding line has retreated up the seafloor slope over the past decade. So in 2011, the grounding line was mapped with remote sensing, which you see as this white star here on these figures. And then it was mapped again in 2016, where you can see these blue stars. And then finally, it is to the point where we see it now at T2, well up above those 2 stars. So these plots here show the melt rate along these 2 transects along the ice base. And the key takeaway here is that in the middle two panels, you can see these melt rates plotted along the ice base. So the key takeaway here is that the flat ice, which you can see shown in blue here, melts relatively slowly upwards at about 2 meters a year, which is consistent with what Peter Davis showed before from the independently measured radar data. However, these crevasses are hotspots of melting where the ice melts laterally or horizontally at about 20 meters a year. And this is because the slope of the ice determines the efficiency with which ocean heat and salt mix into it and drive melting. And finally, we see near the grounding line, the melting is lower because of these colder, fresher ocean conditions and weaker current speeds. So this region for now is somewhat more protected from direct ocean melting.
So the site that I am going to present from is the same as the previous two presenters, Peter Davis and Peter Washam. And what we're looking at on the right is a map view, and the black thin lines indicate the location of the grounding zone, so where it goes from sitting on a bed to floating over the ocean. And anything to the right of that grounding zone in this map is grounded, anything to the left is floating. So I want to zoom in on this red box here. So now looking at the figure on the left, what I did was collect reflection, seismic, and radar data. And what these data do is help you look at what material is beneath the ice. And so what we see in these signatures in the grounding zone and a couple kilometers upstream, so further away from the ocean, there's a lot more variability in that basal material than initially expected. There's regions where it looks like it could be rock, and then regions where it looks like it could be wet till, like mud, essentially very wet mud, and even some regions where it could be thin water. So what this looks like is happening is a mechanism called tidal pumping. And if you imagine you have a 2D cross-section of ice, ocean, and sediment interacting, what happens is when you have low tide, the floating ice shelf portion sinks down, and this acts with the lowering water. And this acts kind of like a lever and can actually pull up a section a little bit inland that can pull water in. And then the opposite happens when you have high tide and the water level rises, the floating section rises up, and then a little bit inland, you have a leveraging down kind of phenomenon. And so this up and down motion in the grounding zone and a couple kilometers upstream can kind of pull water in. So the main takeaways from the evidence for this tidal pumping is that we have data evidence supporting that this process is happening, which has not been too frequently observed elsewhere. And also, given the warm water that's beneath Thwaites, this tidal pumping could have really big implications for the melting and stability of the grounding zone of Thwaites. Now, what we're looking at is a 2D profile of the radar data set. So on the right side of the figure is that area where the ice is sitting on the bedrock, and on the left side of the figure is where you have the glacial ice floating over the ocean. And this orange line I'm pointing out here is the ice fin data that the previous two presenters showed, where you have the seafloor and the bottom of the ice shelf with the crevasses in it captured. So now we're looking about 5 kilometers further downstream on the floating ice shelf. And I want to talk about this basal feature here. This is very large compared to the crevasses we were just talking about. So the interesting thing about this feature is that it's in ice that we think was grounded upstream about a decade ago. So how did such a large feature form so quickly? So if you imagine you have a chunk of ice floating over the ocean, and that ice has layers in it, if you somehow rapidly melt and remove a section of the bottom of the ice shelf, then what has to happen is the ice over top that thinner section has to float a little bit lower. Imagine ice cubes in your glass of water, or a large iceberg, right? Bigger stuff floats higher. So it has to sink down, and you'll see this reflected in the internal layers, and that could potentially force open some crevasses in the top there. And then, much like Peter Washam showed upstream, you can get warm water in there. The melt rates on those sloped surfaces and those crevasses is more rapid, and you can propagate the formation of this feature upwards. So this is what I think is happening here. And the takeaway is that the existence and possible rapid formation of such features could have implications for the long-term stability of the ice shelf. So how long the ice shelf will be around to provide that buttressing impact for the ice upstream.
Glaciers like Thwaites could also dramatically retreat through processes called ice cliff failure and marine ice cliff instability. In this figure, a vertical ice cliff may be exposed if we lose the ice shelf, so the part that's floating over the ocean. There is also a region of the Thwaites terminus that currently ends at a cliff. This is shown in the box in the inset. This area is not retreating through ice cliff failure yet, but we want to know, will ice cliff failure become a factor in the future retreat of Thwaites? Using a unique 3D modeling workflow, I have quantified calving retreat rates that can be expected from ice cliff failure. Retreat through ice cliff failure is modest when ice cliffs are around the height threshold for failure to occur, but the rates of retreat dramatically accelerate as ice cliff height increases. From these retreat rates, I have derived a simple equation to represent ice cliff failure in larger scale models that look to simulate the future of the entire Antarctic ice sheet. My 3D glacier modeling work also shows that ice cliff failure will occur through a range of what I call modes. Some of these examples being shown here with the termini of these idealized glaciers failing through tensile and shear failure. My work was conducted with a model workflow that paired two 3D models. First, glacier flow was simulated in Elmer ice. And after varying durations of flow, I would test for ice cliff failure in a model called HIDEM. This unique workflow allowed me to quantify how long of a period the glacier needed to flow over before that failure occurred. And this was not possible before and led to our retreat rate calculations that I showed earlier. So we are interested in ice cliff failure, especially because it can be a component of marine ice cliff instability. And this figure is showing that after we lose any extending ice shelves and get to a situation like in T3, we'll have a vertical calving face and ice cliff above the waterline. And if that outward pressing stress that is represented by the horizontal arrows is great enough, then that stress could overpower the strength of ice, and that would lead to an ice cliff failure event. Now, if a taller ice cliff is exposed after each ice cliff failure, then that outward pressing stress is going to grow and grow, accelerating collapse and potentially initiating the self-sustaining process that we call marine ice cliff instability. And this scenario would be more likely to play out over regions that have a reverse sloping bed and large thickness gradients as we move inland, like the situation shown here. And dauntingly, much of Thwaites Glacier and the West Antarctic Ice Sheet sit over such reverse sloping beds. We found that retreat rates are modest for cliffs that are just at the height threshold for ice cliff failure to initiate. There is a great acceleration to alarmingly fast retreat rates for really great ice thicknesses. We present a solution to represent ice cliff failure in these large-scale ice sheet models.
In terms of this year, we've seen Thwaites continue to evolve. And in fact, just in the last few years, the pace of acceleration on that ice shelf area that Aaron talked about has increased. And so, as well as the cracking, we've seen the fracture grow. In fact, just yesterday, we got some high-resolution satellite pictures of our field site to take a closer look at just how close some of the fractures have come to where we're planning to camp. And they're still comfortably far away, but things are evolving rapidly there. In terms of what's happened at Thwaites over the last decade or so that continue to underscore how important the glacier is. It's continued to increase how much flux of ice it's putting into the ocean. It's around 50 billion tons per year, still a relatively small fraction of sea level rise, but as this whole presentation has underscored, it's upwardly mobile in terms of how much ice it could put into the ocean in the future if some of these processes continue, particularly to the point where the ice-ocean interface is much thicker ice, and therefore some of these other fracture processes begin to take hold.
I just wanted to pick up on what Seth is saying there. I mean, for better or worse, we've labeled this thing the Doomsday Glacier, and you guys are talking about something happening that's really dramatic. Not 50 years from now, 100 years from now, but almost in the next political cycle, the next 5 to 10 years. I assumed that this was, some way off, but you're telling us here today that we're about to see really quite dramatic change in one of the biggest glaciers in the Antarctic. Can you comment on that?
I'll say a few words. Yes, you're right. There's going to be a dramatic change in the front of the glacier, probably within less than a decade. A lot of studies, both published and what Aaron has shown today, point in that direction. When that happens, the fast flow part of Thwaites is likely to widen because the bracing on the east side will be gone. It may still take a few decades before some of the other processes that accelerate the ice flow and the retreat take hold. It will, though, accelerate the pace and effectively widen the dangerous part of the glacier.
The end member, the way I see it is that as Ted said, it's going to accelerate to match that faster part of the glacier, which means that this 1/3 that is flowing more slowly now could potentially triple in speed over the next, who knows how long, decades to century. And that's the part that we don't have a good handle on, is how fast the acceleration will happen. But if it accelerates to match the other 2/3 of the glacier, that's a tripling of speed of this section of the glacier. What will control that acceleration is some of what the other ITGC groups are studying. So some of the upstream, how it's moving along the rocky and sediment bottom of the ice, and how the sides of the glacier, how slippery those sides of the glacier are, where it is attached to the other ice. And there's bedrock. There's a lot happening upstream, essentially, that will moderate how quickly that acceleration can happen. So the end member is that it could triple in speed, but the rate at which it will get there depends a lot on what's happening upstream, and that's what our partners in the TIME and GHOST teams are studying.
That eastern ice shelf, what sort of area are we talking about from the grounding line to the pinning point? What area is relatively stable there on that?
It's about 1,000 square kilometers. So it's 40 or 50 kilometers long and 30-ish, 20 to 30-ish kilometers across. The ice tongue is already pretty loose, and it's flowing at 2 kilometers per year right now across about 80 kilometers width. And then this section we're looking at is another 40 kilometers, where right now it's only flowing at about 600 meters per year. And it could, that's why I said the tripling in speed over that 40 kilometers could triple in speed when this all releases.
But the big change, like you're saying, would be the loss of the ice shelf. And that's going to look like a bunch of icebergs drifting off to sea, but then behind it, we'll see the glacier pick up speed and the grounding line retreat further.
The threshold for ice cliff failure to start occurring, we find to be around 130 to 140 meters. Tall. The extreme scenarios that I was showing in that plot are something like 400 meters, of ice cliff height. Really, what I was showing that, being the kind of key factor if we hit that unstable retreat or not, is that thickness gradient. So how fast the ice is getting thicker inland is really going to determine if ice cliff failure takes off into that self-sustaining marine ice cliff instability or not.
So the ice has to be thousands of kilometers thick to still touch the seabed and support a cliff like that.
Yeah, so those are extremely extreme scenarios, but it just does show how this takes off, if we were to retreat really, really rapidly, and how it would become an accelerating process. I find actually the other third of the glacier to be really interesting for this process. It's right now that part of the glacier that doesn't have an extending ice shelf or an ice tongue, is at a vertical cliff at the moment. And it's not tall enough to be, in ice cliff failure territory at the moment, but it's also sitting on a bit of a high in terms of the glacier bed or the seafloor there. So if we push that back a little bit through melting and kind of normal calving, we could dip into that basin. And that's where there's a potential for this ice cliff failure to initiate. So all to say that, every third of this glacier is interesting and potentially susceptible to major changes.
In fact, the thing that got everyone's attention was the fast-flowing 2/3 of the glacier and the fact that the ice descends basically, or the bedrock descends into a really deep basin. And so those numbers for ice cliffs, super high ice cliffs, we haven't seen those yet on Earth. We've seen things that come close, but Thwaites has the kind of geometry that could really make at least the middle range of those extreme heights possible. Yes, it's daunting. It's a bit unsettling, especially standing on the ice and looking onto the ice sheet and seeing that this huge area from one side of the horizon to the other is moving at you at about a mile every year. And all by itself, this one glacier could impact, it's big enough to impact sea level significantly.
Our predictions right now, based on current rates of these processes happening, is that the ice will lose contact with the seamount within about a decade, but the fracture propagations are happening more quickly, and it looks from the satellite imagery that we've been following that it's going to essentially bypass that pinning point and start fracturing and falling apart despite that pinning point attachment, that seamount attachment. So the fracturing could happen within 3 to 5 years at some of the current rates, but the stresses are changing on a week-to-week basis from the satellite imagery that we keep getting. Everything looks a little bit different every time we get a new image, which is really fascinating to see. And as Ted said, it's a little bit unsettling.
You know, given that this had been previously the more stable part of the Thwaites ice shelf, can you talk a little bit about the process of realizing sort of what was happening, the speed at which it could be happening, and kind of like this last stable buttress is no longer as stable as it had previously been? Like, what was there a moment either on the ice or looking at your data where you sort of realized like, oh, this is unsettling, as multiple of you have put it? And also, how surprising is that? Like, is this something you were expecting to happen eventually? Is this happening faster than you'd been anticipating?
I'll just say that satellite mapping of Antarctica, and I showed a satellite map that had red patches, and Thwaites is in the center of one of the bigger red patches. Other means of using satellites really identified Thwaites and the ice shelf as a place that was changing. There really hadn't been a lot of visitors on this part of Thwaites ever. But the satellite data helped show that this was an area that needed to be focused on. So in terms of a realization, I think there's been several for all of the field work. I mean, I think there were some thrilling things that came out of the borehole science right at the grounding line, with the robot looking around, poking around, and also the long-term measurement showing ocean eating away at the ice sheet, sort of right before our eyes.
I think one of the points that I realized that this was going to happen a lot faster than I thought was when we were in McMurdo 2 years ago, and we started looking in detail at high-resolution imagery of the field site we were planning to go to in the middle of this, what looked like the most boring part of the eastern ice shelf, because that was also the safest part. So we had designed our field plan around going to a very nice, safe part of the ice shelf. And we got these satellite images in that showed this crack propagating, this big rift in the ice propagating straight towards our field site. And as we're sitting there around the big table looking at these images and watching the propagation of this crack through a sequence of images, we actually just all had to take a pause and just understand whether or not this crack was actually going to break through our field site while we were out there. And once we kind of took that deep breath and looked at it again and realized it wasn't quite going that fast, we were okay, but it still was hugely surprising to me that this was rapidly changing that fast. So I do remember that moment.
What's our nickname for that crack?
The dagger.
The dagger.
So I think to jump in and kind of talk about the ocean perspective, I suppose one of the things is that we don't know what's happening in the ocean until we drill through it. We can't observe the grounding line from space. We can't send an autonomous vehicle from the ice front there because it's too far away. So I think a lot of what was surprising for us was because we didn't actually know what to expect in the first place. It was the first time we drilled into this grounding zone. So I think the large amount of heat available, that was expected. I think we would have been incredibly surprised if we found something that didn't have that sort of characteristic. But I think what is surprising is how slow the flow speeds are, and kind of arguably in terms of the vertical melting, how little it is melting in the vertical. Of course, what is interesting, I suppose, it doesn't mean it's not changing quickly. I think we've heard a lot about how the ice shelf is responding rapidly, despite the low melting at the grounding zone. So I think that's quite a key message. And it goes to show kind of what Erin's talking about, that there are these three processes, and perhaps the ocean at the grounding zone is not perhaps the one that's driving the major changes on thwaites, and it's the kind of the ice dynamics and the pinning points. But I will hand over to Peter, because I think some of the other surprising things are what Iceland found, and the kind of the difference between the vertical and the horizontal.
Yeah, and another thing that was really nice to see is that the seabed is sloping upwards towards the grounding line. However, we still see about 1 to 2 kilometers of grounding line retreat over the last decade. And typically we consider that configuration of seafloor slope to be more stable. So then you have to look upstream of where the current grounding line is to get a better read on how that might evolve in the future. So certainly it was a bizarre environment to send instrumentation into, and Iceland was really critical in measuring, or sort of getting a good estimate on what's happening on all these different slopes of the ice space relative to the ocean forcing. And so the vertical melting, if you sort of take all that region and integrate the area times the melt rate, you see that the vertical melting, this sort of slow upwards melting is the majority of the melt. However, there's these sort of hot spots of melting where you can melt sort of horizontally. And what's sort of concerning is that when you have crevasses and other features spaced relatively close together, that horizontal melting begins to be a little more important when you can sort of mesh things together, as what Lizzie showed with that basal feature downstream. So certainly there's this localized hot spot of melting in these crevasses, and even on these smaller features where something with a steep vertical face can just melt sideways and take out chunks of the ice, but it's still a localized process. However, it's important, and it definitely plays a role in the state of the ice. So yeah, I think that's all I'll say for that.
So if you're talking about ice cliff failure, there are some glaciers in Greenland that come close to this sort of process. And in fact, that kind of kicked off some of the modeling and the interest in the whole concept of what happens with really tall ice cliffs. And in fact, one thing to say is we're watching a world that's doing things that we haven't really seen before. I mean, the ice is responding in some ways that are surprising us because we're pushing on climate extremely rapidly with CO2 emissions and greenhouse forcing. So in terms of refining our projections, that is a goal of the ITGC and a goal of a lot of groups that are working on ice sheets and what sort of things cause them to retreat faster in a warming climate. I think we are going to make some progress in terms of forecasting how thwaites will unfold, in large part due to Anna's work, and she mentioned her colleague, Jeremy Bassis. That's an important component, and the thing that I want to draw spotlight on her work is the fact that getting a time, a rate basically for how fast fracturing happens is kind of a breakthrough, because a fracture process is very difficult to model, and getting a time for something, when something will crack, that's a fundamentally difficult problem in physics.
By joining these two models, I was able to quantify what I call that time to failure. So what Ted was describing as how the fracture that happens after the glacier flows for a certain amount of time. And that was a major jump, in the modeling of ice cliff failure, because before many assumptions need to be made about when that failure occurred. So that allowed us to calculate those retreat rates that I was showing and derive that equation that can now represent ice cliff failure in a more informed manner in these large scale ice sheet models.
We have actually not so much suggestions or recommendations to policymakers. Those are, I think, fairly obvious and fairly broad. That's a thorny issue, but we have reported to the British Parliament, for one, and other groups that are interested in informing Congress for another, about the results of ITGC and the progress of the research there. And that's an ongoing thing. I kind of stumbled over one of my last slides, which was intended to show that our data gathering and then our synthesis is intended to inform policymakers through predictive papers that talk about both the future behavior and lessons learned from past behavior of Thwaites Glacier. That's also a part of ITGC. That will help characterize what the next century is going to be like from this part of Antarctica. We think it's going to be led by changes in Thwaites Glacier.
So, what do we do about it? It's very hard for me emotionally to be here talking to you about this, because I feel like I'm talking about the sky is falling. If the 20 feet collapse, if the ice sheet collapse and 20 feet of sea level rise is unstoppable, and there's really no reason to think it isn't. Ice is a very simple model. You got water, you've got gravity, and you've got temperature. You increase the temperature, the ice melts. And gravity is pulling down on the ice sheet too. So what it means is we have to now figure out how to slow this down as much as possible. I believe what we have to do is get off fossil fuels as fast as humanly possible to get back down to that range of 170 to 280 parts per million, which is why I disagree with the 350.org people who say 350 is a safe level to get down to. 350 isn't safe because it's not the natural tolerance. 350 was based on the idea that if you got down to 350, you could limit the global temperature increase to 2 degrees centigrade above pre-industrial. But you can't control the thermostat of the Earth like you can your living room. What you have to do is think in terms of what is causing the heat to build up and get that fuel back down. And I think of CO2 molecules and the other greenhouse gas molecules as little heat sponges. So the more you put in the atmosphere, the more heat is held in. And a lot of people say, well, it hasn't warmed up that much. It's true compared to what a lot of people predicted, but that's because 90% of the heat was absorbed by the ocean. And that's also why West Antarctica is melting faster and faster than anybody ever imagined before. The first thing is to buy ourselves as much time as possible. But there's not a lot we can do in terms of greening our personal lifestyle. Well, really, anything that anybody's proposing is not going to stop that 20 feet of sea level rise. And because there's so much variation in what the scientists say, people are still quoting the IPCC report that says we've got 1,000 to 3,000 years before it's going to melt. People confuse the melting of those 6 glaciers on the Amundsen Sea and 4 feet of sea level rise with, if West Antarctica melts, we're only going to have 4 feet of sea level rise. But we're going to have 20 feet of sea level rise. And now we have 3 reports saying that's all going to happen over the next century. We're going to have 10 feet of sea level rise over 50 years, 70 years, or maybe just 33 years. So we've got a couple of major tasks we have to do. In a general sense, we have to start thinking, okay, how are we going to relocate a couple of billion people who live on the coasts of the world? That's a bigger project than I can think about right now. I don't know how to do that, but that's what we, my fellow human beings, have to figure out over the next few decades. We have to figure out how to relocate all of civilization. All of our harbors are going to have to be rebuilt somewhere else. We can't really plan to do any kind of industrial development on the coast. In fact, I think what we should do is we should start encouraging people to move inland and then turn the coastal areas into agricultural areas. And that way we can grow food in areas. You know, I used to live in Los Angeles, and there's a lot of great farmland underneath the pavement. And so as people move away from there, you can pull up the pavement and you can start farming there. And then when sea level does start to kick in, see, here's the problem. What people really aren't talking about is that when West Antarctica goes, how fast is that going to happen? And if you look at what happened during the Madhouse century and what happened 1 million years ago, things stayed pretty hunky-dory, and then they suddenly started to go up 8 inches per year. So that's something we can't wait for. We can't wait until we actually see the sea level rise before we do some things like shutting down our coastal nuclear power plants. If you look into how we decommission our nuclear power plants, there's a procedure called Safe Store, SAFSTOR. And it takes 60 years to decommission a nuclear power plant. Turn off a nuclear power plant, you have to let those nuclear materials cool for many years before you can start to disassemble anything. So that's why I'm arguing that we have to, it takes 60 years to decommission them. They're going to be flooded in 25 to 35 years. That's a problem because there's probably 50 nuclear power plants around the world. There's 400 around the world. But there's probably 50 of them that are on coastlines, maybe more. So what I'm seeing is 25 to 35 years from now, 50 Fukushimas. 50 Fukushimas. And the only way to prevent that is to start decommissioning them now. And that means 2 more things. We have to more than double the speed of decommissioning. We have to shorten that 60-year period down to less than 25 years. And we also have to finally decide what we're going to do with the nuclear waste. Because if you want to clear the coasts of the nuclear power plants, where are you going to put their nuclear waste? So now we have a situation where we have politicians to this day that are still denying that global warming is real. Now, I believe that the people who kept us on this fossil fuel path, so that we got up to 409 parts per million, and so that our ice sheets are collapsing, it's their policies that caused that to happen. So the climate denialist policies of keeping us on fossil fuels are, to me, traitorous. Because what is a national security threat? A national security threat is usually thought of as a military, a foreign military coming and attacking us, and then we have our military that fights them. But if you think about, well, what are they doing? They're actually protecting our property. Remember, the Russians were supposed to come and take over America, or the Chinese with their huge army were going to come and take our property. So protection of property and protection of our lives, to me, are what national security is all about. So I would like to reframe national security, because now what's happened is these politicians have guaranteed that every square foot of our coastlines, all of that property, personal, private, and public property, is going to be destroyed. Not only ours, it's also this incredible act of war, because there's 131 other countries that have ocean coastlines. Because of the greenhouse gases that have been burned by the industrial nations, all of those countries are going to have their coastlines under 20 feet of water by the end of this century. So we need a way politically to get off fossil fuels. And I've been involved in the Bernie Sanders campaign. Before Bernie coined his political revolution, I was arguing for an electoral revolution. I believe that all of the Republicans and most of the Democrats who are in Congress now, who have all of this big fossil fuel money, have to literally be removed. And they have to be replaced by citizen leaders from our community of whichever party, but people who are going into Congress to really take care of the people and take care of the planet. And so an electoral revolution, I believe, should focus on replacing members of Congress. In 2006, when the Democrats took over the House and Senate, there were about 17 seats that they won by 5,000 votes or less. And I thought, well, you can give credit to the bloggers for getting that 5,000 votes. So what if the next time around we started to focus on the races that we lost by 5,000 votes? Those districts would be worth investing our activist time in organizing around year after year after year until we oust the conservative person who's in there. And then you could, work on the areas where we lost by 10,000 votes or less. You could do this also in the primaries. I helped start 2 Green parties, the Citizens Party in 1980 and the Modern Green Party in 1985. And there are a lot of greenish progressive people in the Democratic Party and environmentally oriented people in the Libertarian Party and independents. And in the primaries, you could do the same kind of organizing, and instead of a centrist Democrat winning, you could have a more progressive Democrat or a greener Democrat win. Congress is where the policies that have gotten us here were developed. And Congress is where the solutions are going to have to be developed. We're going to have to come up with policies, a national energy policy that gets us off fossil fuels probably in 10 years or less. I mean, think about it. That seems extreme, but we're already at 409 parts per million. It's like a guy who's doing meth, 20 times a day. You can't just say, well, cut back to 19 times a day if you want the guy to live. No one else is talking about getting off of fossil fuels. Currently, President Obama's plan, which is the only one that Democrats are talking about, is about getting off or getting down 90% by 2050. Okay, 33 years. But we could have 10 feet of sea level or 9 feet of sea level rise by then. So it's too late. So we have to do something that's not just reform measures anymore. So I'd like you to ask yourself, when you go to vote for anybody, whatever party, and you think about global warming, you think about the ice sheet collapse, ask yourself, could this person going into Congress, could they actually do something that will make a difference? In other words, are there reform measures? Can they change something in the budget? Can they fund the Energy Department or the EPA more? And will that do it? Those are reform measures. And I think the answer is no. That's why Bernie and I both use the term revolution. Now, we're not talking about anything violent. We're both talking about using the ballot box for revolution. But what that means is we literally have to think about replacing a class of politicians. And it's the reason why I think a lot of people had problems with Hillary Clinton, because they recognized that Hillary Clinton was being backed by these same fossil fuel interests. She's for fracking. And so we have to think in terms of plutocrats. Plutocrats are basically a class of elites. It's both the richest people and the politicians that they fund. So think of it like a mansion. Politicians go to a mansion and they hang out and they have a party with all these rich people. And those rich people give them money and then they split and they're going to get into Congress and they're going to pass bills, but they're not going to pass bills that these rich people don't want. And that's the way it works with both those parties. So we really have to think about ousting the plutocracy. And I hope people will use that word, plutocrats, plutocracy, because that's really what's going on. As long as we're focused on Democrats versus Republicans, we're losing the game. Democrats and Republicans and everybody else have to come together. We are all human beings on this planet, and we all have the same threat. Republicans, Democrats, Independents, Libertarians, Greens, their property is going to be wiped out by this sea level rise. This is just the greatest crisis humanity has ever had to face. And it means we have to do things that we haven't done before, right? So that's why I think reform won't work. An electoral revolution is the only way to go. That's it. I hope if you want to support this Clear the Coast Roadshow and getting the word out, you can check my website, andycaffrey.org, and you can get more information there. And if you'd like to finance the cost of doing this roadshow, please go to PayPal.me/Andy Caffrey. Thank you very much. So then the question is, well, did West Antarctica melt, and then what happened? What caused the sea level to drop 50 feet? Well, you've heard the concern that the melting of the sea ice in the Arctic causes the top of the planet to be darker, and it absorbs more heat. Well, I think that's causing more and more warming, and it's causing more melting of the sea ice. And it's also causing more melting of Greenland's ice sheet. But I think what happened 120,000 years ago was the exact opposite. You see, you've got this sea ice phenomenon in Antarctica that we showed you in the first picture. That doubles the area in the winter that's white, that's reflective. But it always melts back. That sea ice is only about 4 feet thick. Now, what happens if the ice on the continents were to be unleashed and expand over the same area? For example, most of Antarctica is between 1 mile and 3 miles thick. And it's surrounded by ice shelves. 97% of it is surrounded by ice shelves. And if these ice shelves, which float on water, if they melt, there's no real problem with sea level. But they're holding in the continental ice. Now, the way to picture this is, imagine making pancakes. You take your batter and you pour it down, right? So it pours down and then the pancake expands outward. Well, that's happening with the ice, except with Antarctica, it's got this ring holding it in, but the gravity is still pulling down and would still cause it to expand outward. So what I think happened was, 120,000 years ago, these ice shelves broke off, and then this 3-mile thick ice, it basically became maybe a 1.5 mile thick ice, but it doubled the area. And that caused the Earth's albedo, that's the reflectivity of the Earth, to increase, and did the exact opposite of the Arctic. It reflected more of the sun's heat away, and that caused a cooling that triggered us going into the last glacial period, because that's exactly what happened. 120,000 years ago, when the sea level went up and then went down, we went into the last glacial period. And we had an ice age for 100,000 years.